Okay, so in this section, we are going to talk about inductance. And we're going to start by looking at the concept of mutual inductance. So here we have a coil of wire that is connected to an AC generator. So current is going to be flowing through this coil and producing a magnetic field. We know from past chapters the magnetic field. We were able to find the magnetic field created by a solenoid. But since it's an AC generator, the current is going to be going back and forth, so the magnetic field also will be switching directions. So we have created a changing magnetic field created by the changing current going through this primary coil. Therefore, there's going to be a changing magnetic field. If we now put a secondary coil next to the primary coil, it's going to feel a changing flux through this coil due to the primary coil, and that changing flux will therefore produce an induced EMF in the secondary coil, and that's the voltage that we see here. So what we find, what's called mutual inductance, is that the changing current in the primary coil induces an EMF in the secondary coil. So now we're going to use Biot-Savart law to find the magnetic field created by the primary coil. So we know this is Biot-Savart law. We have to do this integral to find the magnetic field at this point in space where the secondary coil is due to the primary coil. So the magnetic flux through the secondary coil is due to the magnetic field created by the primary coil. So the flux is going to be equal to the magnetic field of the primary coil dot dA2, the surface area of the secondary coil. Can't get it to go to the next. Okay, here we go. So now I just plug in B1, the magnetic field that we'll find using Biot-Savart law due to the primary coil. We can take out the current. And now I'm going to define something called mutual inductance. I'll call M21, and it's going to be equal to this big integral here. So that we can write the flux going through the secondary coil is equal to, it's going to be proportional basically to the current going through the primary coil times this mutual inductance. So the induced EMF in the secondary coil is due to the changing flux. So if we now substitute phi2 is equal to di M21, we get the induced EMF in the secondary coil, E2, is equal to minus this mutual inductance times the change of current in the primary coil. And M21, this mutual inductance, this M, we can see from what it's equal to, it depends on the geometry of the coils. And the unit, the SI unit for inductance is Henry's H. Okay, so we see that the induced EMF, it's going to oppose the change in flux. This is Lenz's law. So for example, if the current going through the coil is increasing, the increasing, well, we'll talk about this more actually before I want to get to self-inductance. So we have now just one coil instead of two coils, and we have an alternating current that is going through the wires in this primary coil, in this one coil, and that's going to create an alternating magnetic field. So there will also be a changing magnetic flux in this coil. Not only if we had a secondary coil is there a changing magnetic flux in the secondary coil, but even in itself, in the primary coil, there's also a changing magnetic flux. So there will also be an induced EMF in the primary coil. And this is called the self-inductance. Instead of M, we have L, which is called the self-inductance, and it has the same units of Henry. So we have a induced EMF that is going to occur when we have a changing current in a coil. Okay, so now we can talk about how this induced EMF is opposing the change in flux. So, for example, if the current going through the coil is increasing, the increasing magnetic flux induces an EMF that opposes the original current and tends to stop the increase. So you need to basically fight against the self-inductance to drive the current through the loop. The bigger the circuit self-inductance, the harder it is to push current through or to change the current in the circuit. Okay, so you can kind of think of an inductor, it's similar to a resistor in that it resists current flow, but for an inductor, there's only a resistance to current flow when there's a changing current. And a circuit that has a significant amount of coils is called an inductor. And the symbol for an inductor in a circuit diagram is this little coil here. So you'll have your first example problem with an inductor and a capacitor in a circuit. Now we're going to look at the energy stored in an inductor. So an inductor in a circuit can store energy just like a capacitor. So we plug the inductor with inductance, let's say L, into an AC source. And we're going to look at the segment of time when the voltage is increasing from 0 to a maximum value, let's say here, V naught. And we know that if you have a changing voltage, you're going to get a changing current, right? You're starting from a 0 current to some current value, a non-zero current value. So we have a changing current. Therefore, we also have a changing magnetic field. Therefore, we have a changing magnetic flux through the coil, and this produces an EMF across the inductor. And Lenz's law says that the induced EMF is going to be opposite to that of the voltage source. So the induced EMF opposes the AC current source increase in current. So the AC voltage source must do work in order to push charge against the induced EMF. And the work done by the AC voltage source is stored in the inductor. So now let's find the energy stored in an inductor. So first, we're going to look at the magnitude of the work needed to push a dq of charge across a voltage E. So that's just going to be equal to dq times E, the EMF. We know that E is equal to L di dt. I'll multiply by dt over dt. So I get a dq dt, which is just equal to I, the current. So I have an I L di, and now I can take the integral of both sides. So the work is equal to the integral of Li di, which is 1/2 Li squared. So the work done by the AC voltage source is stored in the inductor as energy. So the energy stored in the inductor is 1/2 Li squared. So in this example problem, you're going to find the energy stored in a magnetic field using these steps I provided. What you'll find is that the energy stored in a magnetic field, B, we integrate over all space, is equal to 1/2 mu naught integral of B squared d tau. And this, if you look back, is very similar to the expression we found for the energy stored in an electric field. Instead of the mu naught, we have an epsilon naught for the electric field. Now, then you'll do another example problem. And that is it for this set of lecture slides.